Experimental study of photoelectric effect. This is an evacuated glass tube. Cathode, suitable photosensitive metal or a photosensitive material is pasted on this cathode, and this is anode. This is the side tube, quartz window. This is how evacuated glass looks like. Cathode is connected to a battery and then the anode. C for cathode. This cathode is connected to negative of a battery. Negative, positive, negative, positive. And this symbol represents variable source. This is battery. Along with this arrow, this represents variable source, variable voltage source. To measure current through the external circuit, ammeter is used. Usually, current involved in photoelectric effect is very small. It is in microampere. Therefore, this is a microammeter. Microammeter. BA stands for battery, variable source. This is anode. This is quartz window. Why quartz means? Quartz is transparent for ultraviolet, visible and IR. Since this is an experimental setup, it is always better to have that arrangement which can allow all the radiation. All the radiation means UV, visible and IR to pass through. Okay. If we use glass here, glass is opaque for IR as well as UV. Means glass window will allow only visible light to pass. So that's a sort of restriction for the experiment. Since it is for the experimental study, quartz is used. This is side tube. This is evacuated glass tube. If radiation of suitable frequency, so this represents radiation, radiation of suitable frequency or energy falls on the photocathode, and if energy of incident radiation is sufficient to remove electrons, then the emitted electrons are attracted towards the anode, because observe, this positive is connected to anode, means this anode is at positive potential. It is at positive potential means this can attract electrons. Negative is connected to cathode. Negative. So cathode is ready to expel electrons. At the same time, anode is ready to attract electrons. So electrons can travel to anode, and these electrons are photoelectrons. Always remember, we cannot see electrons, we cannot see radiation. So this is pictorial representation. If radiation of suitable energy falls on the cathode, suitable energy means energy greater than work function, then photoelectrons are emitted. They are attracted towards this anode. If anode gathers electrons, then there is a small current in the external circuit. That current is responsible for deflection in the microammeter. If there is deflection in the microammeter means we should think that there is emission of electrons. If deflection is zero, then it is our job to think that there is no emission of radiation. Okay. ಏನು ಮಾಡಬೇಕಪ್ಪ, ನಾನು ಅಲ್ಲಿ ಶುರು ಮಾಡಿದ್ದೆ, ನೀವು ಹಿಂಗೆ ಮಾಡ್ತೀರಾ. ಎವ್ರಿ ಟೈಮ್ ಐ ಆಮ್ ಅಬ್ಸರ್ವಿಂಗ್ ದಿಸ್. ಏನು ಮಾಡಬೇಕಮ್ಮ ನಿಮಗೆ? ಏನು ಫ್ಲಶ್ ಮಾಡಿಲ್ವಾ? ಮಾಡಬೇಡ. ಲೈಟಲ್ಲಿ ಮಾಡಬೇಕಾ? ಇಲ್ಲಿ ನಿಂತಿರ್ತೀನಿ, ನಾವು ಆನ್ ಮಾಡ್ಕೊಂಡು ಫ್ಲಶ್ ಆನ್ ಮಾಡ್ಬಿಟ್ಟು ಅದೇನು ಹಚ್ಕೊಳ್ಳೋದೇನೋ ನೋಡ್ಕೋಬೇಕು. ಗೀತಾ, ದಿಸ್ ಇಸ್ ಟೂ ಮಚ್ ಗೀತಾ. ಹಾಂ, ತುಂಬ ಬೇಜಾರು ಮಾಡಿಸ್ತೀಯಮ್ಮ ನನಗೆ. ಸ್ವಲ್ಪ ವಾಯ್ಸ್ ಕಂಟ್ರೋಲಿಗೆ ಬರಬೇಕು. ನಿಂದು ಕಂಟ್ರೋಲಿಗೆ ಬರಬೇಕು, ಗಂಡಂದು ಕಂಟ್ರೋಲಿಗೆ ಬರಬೇಕು. ಮನೇಲಿ ಬೈತಾ ಇರೋದು ಮಾಡ್ತಾ ಇರೋದು ಎಲ್ಲ ಬೀದಿಯವ್ರಿಗೆಲ್ಲ ಕೇಳಿಸ್ತಾ ಇರುತ್ತೆ. ಅವ್ರು ಆಡ್ಕೊಂಡು ನಗ್ತಾ ಇರ್ತಾರೆ. ನಿಮ್ಗಳಿಗೆ ಏನು ಅನ್ಸೋದೇ ಇಲ್ಲ ನಿಮ್ಗಳಿಗೆ. ಸಾಕೀಗ ಮಾತನಾಡ್ಬಾರ್ದು, ಹೋಗಿ ಮಲ್ಕೋಬೇಕೀಗ. In the diagram given in NCERT book, in place of variable source, they have used a battery. A battery is represented by this symbol, isn't it? Fine. To vary the voltage, a rheostat is used. And symbol of the rheostat, a resistor symbol with this arrow. Okay. Using this device, we can vary the voltage. And a commutator. Commutator is a 4-terminal device like this, and this 4-terminal device can reverse the direction of current. This rheostat is used to vary the voltage. Commutator is used to reverse the direction of current. and all these things can be done by this variable source. So this symbol is used. Now go through this. The following diagram represents experimental arrangement of photoelectric effect. Cathode is coated with suitable photosensitive material. For suitable photosensitive material, or a photosensitive material is used as cathode. The photosensitive cathode and anode are enclosed in an evacuated glass provided with side tube having quartz window. Quartz is transparent to UV but not ordinary glass. Cathode is connected to negative terminal of the battery. Cathode is connected to negative terminal and anode is connected to positive. A microammeter is used to measure very small current. Voltmeter, if at all used, it is used to measure voltage, and commutator to vary the, and commutator to reverse the direction of current. When radiation of suitable frequency falls on the cathode, photoelectrons are emitted. Okay. These photoelectrons move towards anode, and photoelectric current can be seen as deflection in the microammeter. The experimental arrangement can be used to study the variation of photoelectric current with respect to intensity, frequency, potential difference between the anode and cathode, and nature of the material. Let me repeat. It is used to study the effect of current. It is used to study the effect of intensity on current, the effect of frequency on current, potential difference, effect of potential difference on current, and nature of the material. Experimental observations of photoelectric effect. So first point, photoelectric effect is instantaneous. Photoelectric effect is instantaneous means, if this is cathode, of course there is an entire arrangement. Just to explain this point, this diagram is sufficient only for explanation. Okay. As soon as light of suitable energy falls on the photocathode, there is emission of electrons, and emission of electrons is confirmed by deflection in the microammeter. If there is deflection means there is emission of electrons. Okay. Now, as soon as light is incident, deflection is observed. There is no light, no deflection. There is light, there is deflection. No light, no deflection means it is instantaneous, and the time lag between light incident on the material and emission of electrons is about 10 power minus 8 second, which is very small. For human scale, this time is very small. Therefore, it is almost instantaneous. So we can say it is instantaneous. Quick reaction. Second, for emission of photoelectrons, energy of incident photon must be greater than work function. So phi stands for work function. Work function is the minimum energy required to release electrons, and this work function depends on the material used. So from material to material, work function changes. Okay. And corresponding to work function, there is threshold frequency and threshold wavelength, lambda naught. If frequency of incident radiation is less than threshold frequency, there is no emission. Frequency greater than threshold frequency, there is emission, isn't it? Similarly, if wavelength of incident radiation is less than threshold wavelength, there is emission. If wavelength is greater than threshold wavelength, there is no emission. So this is in second point. Go through second point once. For a metal, photoelectron emission takes place only when frequency of incident radiation is above threshold frequency, and the corresponding wavelength is called threshold wavelength. Frequency less than nu naught, no emission. Lambda greater than lambda naught, no emission. If frequency greater than nu naught, there is emission. Lambda less than lambda naught, there is emission. Threshold frequency is different for different metals. Third point. Variation of intensity of incident light and photoelectric current. Intensity of incident light. Intensity is proportional to energy, and energy of radiation is equal to number of photons, energy of each photon. So energy is proportional to number of photons, and intensity is proportional to energy means this implies that intensity is proportional to number of photons. Now understand, if this is photoelectric effect experimental arrangement, cathode, and this is for the radiation, side tube, like this, right? Here is a battery, micrometer, variable source. Suppose if frequency of incident radiation is greater than threshold frequency, then there is emission of electrons. Suppose 10 electrons are falling, then maximum, suppose 10 photons are falling, maximum 10 electrons are emitted. It is really foolish to use such numbers, because in a beam of light the number of photons involved is very large, but still, to understand the concept, let me use such numbers. Okay, now if 10 photons are falling, 10 photons, P stands for photons. If 10 photons are falling, then maximum 10 electrons are emitted, even less than 10, doesn't matter. If 100 photons are falling, there can be 100, maximum 100 electrons emission. If 10 power 4 photons are falling, corresponding to this, number of electrons also increases. Suppose no photon is falling means 0 photon, then there is no question of emission of any electron. 0 photon, 0 electron means origin. With the increase in number of photons, electrons also increases. If number of photons is doubled, number of electrons also gets doubled, which increases photoelectric current. Therefore, graph of intensity of incident light and photoelectric current is a straight line passing through the origin. Go through once. For frequency greater than threshold frequency, the photoelectric current increases linearly with the intensity of incident radiation. Graph. And photoelectric current is independent of frequency of radiation. So this number, photoelectric current, is independent of frequency, but the only condition is frequency should be greater than threshold frequency. Fourth observation, the kinetic energy of photoelectrons versus frequency. Okay, let us understand through this graph. This is a graph of maximum kinetic energy. Ke stands for kinetic energy, maximum kinetic energy of photoelectrons versus frequency of incident radiation. Frequency denoted by nu. In this photoelectric effect experiment, if frequency is less than threshold frequency, then there is no emission. Let us start with minimum frequency. Small frequency, no emission. No emission means no question of electrons, therefore no question of kinetic energy of electrons. For increase in frequency, still less than threshold frequency, no emission, no kinetic energy. At some frequency, photo emission starts, and that frequency is called threshold frequency, isn't it? Fine. Now, if energy of incident is 3 eV and work function is 2 eV, then certainly 3 eV is sufficient to remove electrons. Supplied is 3, required is 2, remaining is 1. So 1 eV is kinetic energy of photoelectrons. Suppose supplied is 4, required is 2, difference is 2. Therefore, 2 eV is the kinetic energy. Suppose supplied is 5 eV, work function, required energy is 2 eV. Therefore, 5 minus 2 is 3 eV is the emitted electrons, kinetic energy of emitted electrons. Therefore, with the increase of incident energy, kinetic energy also increases. With the increase of incident energy means with the increase of frequency. Therefore, a graph of frequency versus kinetic energy is a straight line but not passing through the origin, because at frequencies less than threshold frequency, no emission, therefore no kinetic energy. So it should be only after threshold frequency. Observe carefully. If I extrapolate, then this curve cuts the x-axis, this curve cuts the y-axis at this point. So this stands for work function. Y-intercept gives work function, x-intercept gives threshold frequency, and the slope of this straight line gives Planck's constant, h. Now go through once. At constant intensity of incident light means you have to keep intensity constant, meaning you have to keep number of photons incident on the photocathode constant. At constant intensity of incident radiation, incident light, when frequency of incident radiation increases, maximum kinetic energy also increases linearly. Observe the graph. This kinetic energy depends on both material as well as energy of incident radiation. Related to fourth point, this is a graph of frequency versus kinetic energy, maximum kinetic energy. It is a straight line not passing through the origin. This y-intercept represents work function, x-intercept is threshold frequency, and slope of the curve gives Planck's constant. Okay. Now, how do we get all this? If energy of incident radiation is E, work function is phi, kinetic energy is Ke max, then Ke max equal to energy minus work function, and energy of incident radiation in terms of frequency is h nu minus phi. This is kinetic energy maximum. This equation is of the form y equal to mx plus c, which represents straight line, and this is y coordinate, x coordinate, m is slope, and c is y intercept. Observe, y intercept is minus phi. Minus phi means negative sign phi. Therefore, this magnitude represents work function. Coefficient of slope is x, or coefficient of x is slope. Along x-axis there is frequency, so this is the variable. So coefficient of variable is Planck's constant. Therefore, m is h. Slope gives Planck's constant. This graph is only for one material. Suppose three different materials are used. That time, graph of kinetic energy versus frequency. I am talking about three different materials, photomaterials. So this is graph for first material. This is graph for second material. This is graph for third material. For different materials, their threshold frequencies are different. Threshold frequency of first, threshold frequency of second, threshold frequency of third. But all of them must be parallel to each other because their slopes should give Planck's constant, isn't it? In coordinate geometry, you have learnt that if slopes are same means they must be parallel to each other. Straight lines must be parallel to each other. Now, fifth point. Students, concentrate on the fifth point. Let us simultaneously plot a graph of photoelectric current versus anode potential. Okay. If this is the experimental arrangement, cathode, anode, cathode to battery, microammeter, this is variable, this is incident radiation, side tube, quartz window, fine. Suppose this energy of each photon is sufficient to remove electrons, and we are keeping voltage fixed. This applied voltage is V, negative. So this is minus and this is plus. If energy of incident photon is 3 eV and work function is 2 eV, then kinetic energy is 3 minus 2, 1 eV. Supplied is 3, required is 2, remaining is 1. So this is kinetic energy. Kinetic energy maximum. If applied voltage is 0, incident is 3 eV, required is 2 eV, kinetic energy is 1 eV. Now applied voltage is increased to 1. This 1 volt potential difference, observe, this is minus, this is plus. If there is an electron and this voltage potential difference is 1 volt, then this electron gains 1 eV. If this applied voltage potential difference is 4 volt, then this electron acquires 4 eV. If this is 6 volt, then kinetic energy of photoelectrons is 6 eV, or kinetic energy of this electron is 6 eV. Okay. See, applied voltage is 1. This voltage is 1. 3 is incident. Utilized is 2. Remaining is 1. That 1 is added to this one. Means this 1 eV is supported by 1 eV by the applied voltage. Therefore kinetic energy becomes 2 eV. If applied is 3 volt, incident is 3, required is 2, remaining is 1. But this applied voltage 3 volt gives additional 3 eV. Therefore along with 1 eV, 3 eV is added. So 4 eV is the kinetic energy. If this is increased to 4 volt, incident is 3, required is 2, kinetic energy is 1. Along with this 1, 4 more is added. So 1 eV plus 4 eV equal to 5 eV. So maximum kinetic energy is 5 eV. So with 5 eV kinetic energy, electrons can reach the anode. Okay. This is first observation. Now, if this is reduced to minus 1, means if this is made positive and this is made negative, cathode is made positive and anode is made negative. Now what happens? This positive will attract photoelectrons back. Now let me start. 3 eV is the incident energy, 2 eV is required, remaining is 1 eV. But this potential difference of 1 volt, reverse 1 volt, is decreasing this 1 volt by 1 electron volt by 1 electron volt. So 1 electron volt is this, minus contribution by this reverse voltage is minus 1 eV. So electrons will have zero kinetic energy and those electrons will fail to reach anode. Okay. For zero anode potential, few electrons are emitted. Few electrons are emitted. If anode voltage increases, number of electrons increases. If anode voltage further increases, number of electrons reaching the anode remains constant. So observe, this is the graph. This horizontal portion is called saturation current. Now anode voltage is reversed. If anode voltage is reversed, then because of negative effect, the current also decreases. If anode voltage further increases, then current further decreases. At some voltage, the curve touches x-axis, means anode current, photoelectric current becomes 0. So at some reverse voltage, current becomes 0, and this reverse voltage is called stopping potential, denoted by Vs. Stopping potential. So this is the graph. This is fourth observation. This is the arrangement, isn't it? Assume frequency is greater than threshold frequency. So there is emission of photoelectrons. If 10 photons are falling, maximum 10 electrons are emitted. In the absence of applied voltage, 1 or 2 electrons will manage to reach the anode. So corresponding to this, there is small current. If this voltage increases, if this potential difference increases, then this becomes more positive, then few more electrons can reach. Therefore, number of electrons reaching the anode increases, means current in the external circuit increases. So current increases. If anode voltage is made 2, anode voltage is further increased, few more electrons can reach. As a result, current also increases. If this is made 3, all 10 electrons are reaching. Means maximum value. You increase applied voltage to 4, only 10 electrons can reach. Increase the applied voltage to 5, only 10 electrons can reach, because 10 photons can give maximum 10 electrons and all of them are reaching. Therefore, we cannot have more than 10 electrons. That is why the curve takes horizontal portion, and this represents saturation current. The cathode is made positive and anode is made negative. Then this cathode will be holding electrons back. Now understand this point, 0 voltage. 0 voltage means 0 current. 0 voltage means there is some current, means 1 or 2 electrons can reach. If voltage is reversed, then this positive will be holding these electrons back. So number of electrons reaching the anode decreases. Suppose this voltage is further increased, reverse voltage is increased. So this potential difference can hold all the electrons back, means current becomes 0. So the reverse voltage where photoelectric current becomes 0 is called stopping potential, denoted by Vs. Now, instead of 10 photons, let us use 50 photons. I told you earlier, using such numbers is foolishness, but still we can understand. That is why I am using such numbers. Suppose number of photons increases, number of electrons also increases, maximum electrons reaching the anode also increases, current also increases. But reverse voltage, stopping potential remains same. So for the higher intensity, we get similar curve but with higher saturation current. So this current is obtained, this curve is obtained with low intensity, and this curve is obtained at high intensity of incident radiation. And for both, stopping potential remains same. Now go through once. When potential of collector plate, that is anode, is 0, the photoelectric current is not 0 because the photoelectrons are emitted with certain kinetic energy. When the anode is made more negative, photoelectric current decreases and becomes 0. This reverse anode where photoelectric current becomes 0 is called stopping potential. Stopping, now few points related to stopping potential. Stopping potential depends on frequency of incident radiation. Stopping potential depends on frequency of incident radiation. Stopping potential is independent of intensity. Stopping potential is independent of intensity. Saturation current increases with the increase in intensity. Saturation current increases with the increase in intensity of incident light. So these 5 points are required, and this is for questions like mention any 2 observations of photoelectric effect, any 3 observations of photoelectric effect, or mention any 5 observations of photoelectric effect. Okay, please go through all these 5 again, understand, and this is the basic of photoelectric effect. Now, laws of photoelectric effect. Based on previous topic observations, we can chalk out laws of photoelectric effect. So first is instantaneous. Photoelectric effect is instantaneous. Second, something related to threshold frequency, threshold wavelength, and work function. For a metal, there is a particular frequency of radiation called threshold frequency required for photoemission. Below threshold frequency, there is no emission. Below threshold frequency, there is no emission. Third point, the rate of emission of electrons is directly proportional to intensity of incident radiation, provided frequency of incident radiation is greater than threshold frequency. That we have understood using this graph, isn't it? Current versus intensity. The rate of emission of electrons means current is directly proportional to number of photons incident, and it is a straight line passing through the origin. For loss, you don't have to mention the graph. Okay. Fourth point, fourth law is related to maximum kinetic energy of photoelectrons versus frequency. Maximum kinetic energy as well as stopping potential increases linearly with the frequency of incident radiation. Provided frequency is greater than threshold frequency. And this is independent of intensity of incident radiation. Kinetic energy depends on frequency. Kinetic energy is independent of intensity of incident radiation. Okay. So these are taken as laws of photoelectric effect. Students, goes through these 4 points and note down. Einstein's explanation of photoelectric effect. Einstein used quantum theory of light to explain photoelectric effect. This quantum theory says energy of a photon is given by h nu, and total energy is n times h nu. So n is 1, 2, 3, 4 number of photons. Okay, we cannot have fractional photon. It should be an integral multiple of h nu, which gives total energy. According to Einstein's explanation, if this is a metal, this is radiation, photon, Einstein said only one photon can interact with only one electron. Because of one photon interacting with an electron, that entire photon is absorbed by the electron. If energy is sufficient, that electron becomes free. Meaning, if energy of incident photon is 6 eV and work function is 2 eV, don't expect this photon to remove 3 electrons, because this energy is sufficient to remove 3 electrons. What Einstein said is, if 6 eV photon is interacting with this electron, then that photon is completely absorbed by this electron, and kinetic energy of the electron could be 4 eV. Out of 6, 2 is utilized, remaining is 4 eV. So 4 eV is kinetic energy of the photoelectrons. Means he mentioned 1-to-1 interaction, 1 photon, 1 electron interaction. He also said there is minimum energy required for the emission of photoelectrons, and this minimum energy is called work function. As a result, observe 6 utilized is 2, remaining is 4. So using this, he gave E equal to energy of incident photon equal to work function plus kinetic energy maximum. I will explain this maximum later. For time being, maximum kinetic energy of photoelectrons. Energy of incident photon in terms of frequency. H nu. Nu is frequency of incident photon. Work function H nu naught. Threshold frequency. Plus kinetic energy is half m v square. This is maximum. Now frequency in terms of wavelength, h c by lambda equal to h c by lambda naught. Threshold frequency, threshold wavelength. Frequency of incident radiation, wavelength of incident radiation, plus half m v square. Or h c by lambda equal to h c by lambda naught plus this kinetic energy can be expressed in terms of stopping potential, E times stopping potential. So this is the Einstein's photoelectric effect equation, and these are different forms. Now let me explain why it is maximum kinetic energy and why kinetic energy is E times stopping potential. This is a metal. I am trying to explain maximum kinetic energy. Okay. This is a metal atom. There are electrons in different orbits, and this is the electron in the outermost orbit. This is electron in one of the inner orbits. Okay. This outermost electron is loosely bound. If energy of incident radiation is 4 eV and energy required to remove this electron is 1 eV, then kinetic energy of this outermost electron is 3 eV. If another photon of 4 eV is incident or interacting with inner electron, which demands 2.5 eV of energy, then out of 4, 2.5 is utilized, remaining is 1.5 eV. Observe, because of 2 photons there could be 2 electrons, and in these two this is maximum energy, and this maximum energy is maximum energy of photoelectrons, maximum kinetic energy of photoelectrons. So in E equal to 5 plus kinetic energy, only this is considered, because probability of emission of inner electrons is less. We are not telling it is 0, inner electrons is less. So in a bunch of electrons, maximum energy is given by this, and work function is defined for valence electrons, outermost electrons. That is why maximum kinetic energy is utilized. And corresponding to maximum kinetic energy, maximum velocity is used. Half mv square, this is maximum. If kinetic energy is maximum, corresponding to this there is velocity, and that velocity is maximum velocity of photoelectrons. Okay. Now, second point, kinetic energy, maximum kinetic energy of photoelectrons equal to electron, charge of an electron times stopping potential. If stopping potential is 2 volt, then kinetic energy, maximum kinetic energy is 2 eV. If stopping potential is 3.5 volt, then maximum kinetic energy is 3.5 eV. Similarly, if maximum kinetic energy of photoelectrons is 1.4 eV, implies stopping potential, corresponding stopping potential is 1.4 volt. If maximum kinetic energy of photoelectrons is 3.2 into 10 to the power of minus 19 joule, then express, students observe, express this kinetic energy in terms of eV. How to express? Divide the energy in joule by magnitude of charge of electron. 3.2 by 1.6 is 2 eV. If kinetic energy is 2 eV, then stopping potential is 2 volt. this is how you should use the equation. That is, this is how you should use kinetic energy and electron volt. Okay, so in that sense, energy E, work function phi, then kinetic energy can be represented as E times stopping potential. So we will be using this in problems. So in Einstein's explanation, Einstein used quantum theory which says energy of a photon is h nu. This is one point. Second point, one photon, one electron. So one photon can interact only with one electron. This concept is second point. Third point, work function corresponding to that threshold frequency, threshold wavelength. Thereby we can write E equal to work function plus maximum kinetic energy of photoelectrons. Next point, he also said corresponding to work function there is threshold frequency. If frequency of incident radiation less than threshold frequency, no emission. This says energy of incident is less than work function. And frequency greater than threshold frequency means there is emission, meaning energy greater than work function. Next 2 points, you can mention intensity affects current. So photoelectric current increases with intensity, and maximum kinetic energy of photoelectrons increases with frequency of incident radiation. This is intensity, this is photoelectric current, this is intensity. Go through once.